Well, welcome back to part 5 of the tutorial. If you have endured the last 2 hours and the last 4 parts and you have come back to watch the 5th part, that makes me really happy. And in part 5, I want to talk about another coding scheme for the unsourced multiple access channel. And this coding scheme is different from what we talked about in the last part. In particular, this uses the idea of spreading sequences for controlling the interference between the multiple users. Remember, in the last part, we used this idea of sparsifying collisions and using a message passing decoder. Here, we're going to use spreading sequences as a way to minimize the interference between users. And we're going to use that in conjunction with polar codes and a list decoder. So I'm going to jump right into describing this scheme. I'll try to move my picture away. So as you probably have seen by now, a running theme in many of these schemes is that we're going to split the message W into 2 parts. And the first part, W sub S, we're going to use that to pick a spreading sequence from a master set of spreading sequences given by S. So we take WS, which is of length B sub S bits, right? So oh gosh, just 1 minute. So WS is of length B sub S bits, and we have a master spreading sequence matrix. So think about S. S is a master spreading sequence matrix. It has 2 raised to B sub S columns, and it has N sub S rows, or each spreading sequence is of length N sub S, and there are 2 raised to B sub S of them. So we pick one of these spreading sequences based on WS, and then WC is encoded by a code. We can really use any code that we want, but here we are going to use a CRC plus a polar code. And I'll talk a little bit about why maybe towards the end. And then we get a binary code word at the output of the polar code, which is just then modulated by a binary phase shift keying. And we'll call the modulated code word as U. Okay. Now, U is of length N sub C. Then what we do is we spread every bit in the sequence U by the spreading sequence S sub J that is chosen using the first part of the code word. So once you have spread the coded sequence U, then the overall length of the code words is N sub S times N sub C. So N will be equal to N sub C, S times N sub C. Just give me 1 minute here. Okay. The code word X is then transmitted over the Gaussian channel. Okay. Now, there is a trade-off in choosing the master spreading sequence to have too many sequences versus too little. And what we do is we choose 2 to the BS, or the total number of spreading sequences in the master list, to be not too large. So what happens is we do account for the fact that 2 users may choose the same spreading sequence with a non-trivial probability. So our receiver will have to be designed to accommodate this probability. Okay, now if you think about this process from the perspective of the spreading sequence, so we have 2 raised to B sub S spreading sequences. And since multiple users can pick the same spreading sequence, let's say that M1 is the set of users who have picked spreading sequence 1, M2 is the set of users who have picked spreading sequence 2, so on and so forth. Now, if you think about what you receive, this can be thought of as saying, we first look at the code words, the modulated, the BPSK modulated code words of the users who pick a particular spreading sequence, and we can add up all these users. And then we can spread, so let's call that as V. And then we can spread the sequence V with the spreading sequence that we have chosen. And then we add all those sequences up, and that should give us exactly Y. Right? It's just another way to think about it from the perspective of the spreading sequence instead of from the perspective of the user. Now, if you think about a matrix whose columns are all the spreading sequences, whose rows are all the spreading sequences, and now if you think about what's going to happen, you're going to receive a sequence of length n, which is n sub c times n sub s. So the first n sub s values here correspond to the first coded bit. And then the next n sub s correspond to the next coded bit, so on and so forth. And now, if you take the received signal corresponding to the ith coded bit, and you construct a matrix Y whose ith column is the n sub s length sequence that corresponds to the ith coded bit, then you can get a matrix representation for what you receive. So this matrix Y, you can see, is simply S times V plus Z. So then the ith column of Y is obtained by taking a linear combination of the spreading sequences. And the coefficients in the combination are given by the ith values of this V sequence, where V itself is the sum of many code words. Okay, hopefully this is clear, because this matrix representation is what we're going to work with. Now, the receiver proceeds in a few stages. And the first thing we need to do at the receiver is we need to identify which spreading sequences are active. Okay, and then what we do is, once we know the spreading sequences, notice that we can get knowledge of this matrix S. Now, once we have S and once we have Y, we can try to form a minimum mean squared error estimate of V from Y and S. And once you form a soft output estimate of the V's, we pass that, we convert that to a log likelihood ratio, and we pass that to a polar decoder. And the polar decoder tries to decode multiple code words that have been added together. So in a sense, it's actually trying to decode a small MAC channel. But the polar decoder is not designed for the MAC channel. It's still designed for a single user channel. If you're able to decode the user's code words, then we go back and we cancel the interference off. So that's the basic idea of the receiver. And since this is the important part of the talk, I will walk you through an example just to make sure that we get the idea correctly. So first we try to form a estimate of which spreading sequences are active. So let's take an example. Let's say we have three users 1, 2, and 3. One picks the spreading sequence S5, and users 2 and 3 pick the spreading sequence S1. So in this case, V5, the sum of the code words who have picked S5 is equal to U1, and and V1 is the sum of U2 and U3, because both of these users have picked S1, right? Okay, now you have your received signal. We try to first form an estimate of which spreading sequences are active. Suppose we make an estimate of 3 spreading sequences. Let's say it turns out that we get S1 correctly, but we make a mistake in estimating the other 2 spreading sequences. We think S3 and S9 are active, and when in fact it was only S5 which was active. Okay, so now what happens? Well, we just assume this estimate of S, and we go ahead and try to form an MMSC estimate of the V's. And we then send that through to a polar decoder. And let's think about what might happen here. So we got this spreading sequence correctly. And since the polar decoder, let's say the rate of the polar code on the decoder are such that you can decode the 2 users who are superimposed on each other, then we can decode user 2 and user 3. So in this case, we can end up decoding users 2 and 3. So once we have decoded user 2 and 3, we can reconstruct the signal, the spread version of V1, because we also know S1. And then we remove that in the interference cancellation stage. Now, once I've removed the contribution, I can go back and try to detect which spreading sequences are active again. So this time I may be able to identify that S5 was active. Perhaps I will get another spurious spreading sequence S15, but at least there's a good chance that I will identify S5 correctly. And now we do the same thing. We run through MMSC detector, we decode the polar code, and then we go back. And S5, if you think about S5, there was no user who picked, I'm sorry, if you think about S15, there was no user who picked S15. So even though in the MMSE stage, we pretend like there was a user, we will realize that the log likelihood ratios are going to be so weak that the code is not going to decode. And in fact, we're going to find out that there was no user who picked S15. Okay. So now in the next few minutes, I'm going to quickly walk through how each one of these blocks are implemented, and that will pretty much what I will do in this part of the tutorial. So the first thing is spreading sequence detector, right? We need to somehow blindly detect the spreading sequence detector, and that turns out to be fairly easy. So what we do is this: for every coded bit I, we compute a dot product of the n sub s length vector that you receive corresponding to the ith coded bit and every one of the spreading sequences. Since you don't know the bit that was transmitted for this, we square the inner product and we form a test statistic by summing this over all values I going from 1 to n sub c. And then we simply sort this test statistic in decreasing order and we pick the best a top few estimate of this. In general, we'll have to pick the size of this list to be a little more than the number of active users. But let's say we pick D elements in this list and to be the sorted ones corresponding to this test statistic. Okay, so that's basically how the spreading sequence detector works. I mean, there is a slightly more fancier version of this that we can implement, but in the interest of time, I won't talk about it. We have a paper where we describe that, and that provides a little more improvement in performance. So the next part is the MMSC detector. So given we have identified a set of spreading sequences, we're going to assume that these are in fact the active spreading sequences, and we're going to construct this matrix. It's just the matrix of active spreading sequences. Now we have Y is SD times VD plus Z. And now we try to form a linear MMSE estimate of V from Y. And that filter is pretty easy to compute. So we multiply Y by this linear MMSE filter, and that gives us an estimate for V, and it also gives us an estimate of the covariance matrix of the error. Now, so what we do is we take the diagonal elements in the covariance matrix, and those correspond to your minimum mean squared error in the estimate. So this information is used to convert the mean squared error estimate or the MMSE estimate into a log likelihood ratio. So essentially, we think of an equivalent channel. The equivalent channel is like saying as though V was transmitted through an additive white Gaussian noise channel, and then we observed V tilde, and we know the variance of this noise, and that's given by the diagonal elements in this matrix. So from that, we can compute the log likelihood ratios for V, and that's exactly what we do. And now once we have that, we go to the polar decoder. So we do a successive list cancellation list decoder, and then we pick the path using a CRC. But the one thing that we are doing that's slightly different from most things is that, keep in mind that multiple users may have picked the same spreading sequence. So what we do have to do is to have the polar code decode multiple users at the same time. And the way we can do this is to think of M users if they have all picked the same spreading sequence. We can think of having these M copies of the polar code, and we can think of these M copies as equivalent to having one polar code over a larger field size. So for example, if we have 2 users, and here is a polar transformation of length 2. So you would have two separate polar codes, and each person would have transmitted the coded bits. Now we can combine two of them together, and we can think of it as a symbol over a 4-array field. And then we can just compute the log likelihood ratio. So for example, all the probabilities that we will pass are vectors of length 4. So from the channel, we can compute the probability that the coded symbol here is a 0, 0, 0, 1, 1, 0, 1, 1. And then we pass that through the polar transformation. And then once you go to the end, we can make a decision individually on each one of the two symbols. And then you can make a hard decision on that, and you keep going down the list decoder. I mean, the successive cancellation decoder. I think that's basically the gist of the decoder. Now, in the last couple of minutes, what I'm going to do is I'm going to give you some insight into how we pick the parameters of our scheme. So what are the parameters? Well, first of all, we need to choose the spreading sequence length. If you remember at the beginning of the tutorial in part 2, I talked to you about why you cannot directly use CDMA to solve this problem. And the problem we mentioned was if I simply used orthogonal CDMA, then what I would have needed is a spreading sequence length, which is very, very large. It would really depend on the total number of users in the network. That's not what we try to do here, right? We try to use a spreading sequence which is much, much smaller in length. And as a result, you don't have orthogonality. This is why we need the minimum mean squared error detector and the successive interference canceller. But then how do you actually pick the spreading sequence length? And how do you pick the rate of the code? And how do you pick the number of sequences in the spreading sequence? So to solve these things, what we did is this. We kind of did something which is heuristic, which is not strictly correct. But here is what we did. We kind of analyzed this process using a density evolution type analysis. In other words, without actually simulating the code, we assumed the existence of a code which will decode a particular received set of log likelihood ratios with a probability P sub E. And this we compute by assuming that this code achieves the meta-converse bound. This is to account for the finite block length fx. And then the MMSC detector, of course, we can get exact expressions for the mean squared error at the output of the MMSC detector. So we can just simulate this process without going through the actual simulations. But it turns out that this is not really accurate because we can't really assume that the probability with which a code word decodes in one iteration is independent of the probability that it decodes in the next iteration. However, we make this assumption just to get some insight into what happens. Now, if you use this kind of approximation and you try to look at the minimum signal to noise ratio that you require as a function of length of the spreading sequence. So the question is, what should I pick to be the length of the spreading sequence, right? So let's take the blue curve as an example. So here there are 200 users. If there are 200 users, and if I pick anything more than, let's say, 200 length spreading sequence, well, actually that's not quite true. So if you take longer and longer spreading sequences, you can get lower and lower cross correlation between the spreading sequences, right? But you can see this is not always a good thing because that comes at the expense of not having enough dimensions for your code, which means you have to increase the rate of your code. So the optimum is not obtained at this extreme. So neither is the optimum obtained at the small length extreme, right? Because when the length is very small, you have too much interference from other users. And indeed, there is a region in the middle where you get the best performance. And that tells you that, it's kind of a non-trivial CDMA scheme is what you need. And finally, I will leave you with some simulation results. So keep in mind that I started this tutorial by saying that we have this benchmark from Yuri Polyansky, and this figure here shows that benchmark. And I'm going to try to plot all the schemes that we have discussed so far and try to compare the polar code with it. So the first scheme is this four-fold aloha scheme of ardent click. That was the first attempt at building a coding scheme for this problem. And then I talked to you about using serial interference cancellation in a slotted aloha type scheme in the last part of the tutorial. That's shown in blue. And then we have this CCS scheme, which Jean-Francois talked about. And then there is the AM plus the tree code scheme of Fengler and Giuseppe Caire and his co-authors. And then the green is the sparse IDMA. This is a scheme that I talked to you in the last section. And then this is the polar coding scheme of Frolov and Marshakov, which improves on the performance of the LDPC code. So this is similar in spirit to the SIC T equal to 4, but it has a polar code instead. And here is the performance of what I just talked about. So you can see that the performance of polar coding plus spreading is indeed substantially better than most of the other results. And in particular, in this regime, it even outperforms the achievability bound, which was obtained using Gaussian random coding, right? I think that's pretty much what I want to talk about. I think I'll skip this. And the takeaways from this part is that we proposed a new scheme. It is a combination of spreading and coding. The coding is done with polar codes. And the reason for choosing polar codes with CRC and list decoding is that it has very good performance for short block lengths. And we chose spreading sequences and used MMSC Detector with serial interference cancellation. And if you think about it, all these are fairly standard components of a 5G system. So it's fairly realistic to be implemented within a 5G system. The one problem with this is that the complexity of the receiver grows cubically with the number of users. So the trade-off here comes between these two. The sparse IDMA that I mentioned here, for example, this one has a much lower complexity than this. So this gain in performance really comes at the expense of higher complexity. I think I will stop here. Thank you for listening.